This presentation is delivered by the Stanford Center for Professional Development.
Great. So today we're going to start in, I guess, for real on this third part of the course, which is on algorithms for solving convex problems. The last topic, which was numerical linear algebra, was just sort of a background for it. It's actually what we're going to, everything's going to be built on top of that. Okay, so today we'll start in on unconstrained minimization. I guess this is on your current homework as well. And actually, maybe I'll make a couple of comments about your current homework. It wouldn't, I don't mind mentioning that it wouldn't take you very long, couple of clicks at most, to actually find source code that kind of solves the problems you're looking at. I mean, in particular, just for the book, we have essentially all of the source code online that we used. So I'd recommend there. So I mean, you probably knew this. But I'd recommend there actually, since the code you're asked to write for the current homework is not long, 10 lines maybe. I mean, it's conceptually it's not a big deal. This is not exactly like a heavy assignment. You should try it yourself first, just to see. But if you get stuck or something like that, you type the right things into Google and 2 clicks away, and there's all the source you want. It does pretty much what you want. Of course, actually, then you have to figure out how to adapt it to your problem and all that. But if you want to see the structure of it, so I just mentioned this. If you get stuck with anything there, you can always look there to see how to do this. You shouldn't get stuck though. Okay, that's just a small comment about the homework. Let's look at unconstrained minimization. So here the problem is very, very simple. You just want to minimize a non-quadratic convex function, smooth. That's minimize f of x. Now, of course, minimizing a quadratic is very simple. Minimizing a quadratic you can do by solving a linear equation, because the gradient of f is affine. And so you set that equal to 0. That's a linear equation. So we're interested in minimizing non-quadratic convex functions, smooth. Well, by the way, there are lots of methods for this. We're going to look at methods that produce a sequence of points. They're all in the domain. And the function values are going to go to this optimum value, p star. By the way, in the case when p star is minus infinity, that means this is unbounded below. You also call this a minimizing sequence. So here, this is called because it's, I mean, in that case, of course, the x's don't converge. Okay. And of course, to minimize a smooth convex function is the same as solving the equation, which is that the gradient's equal to 0. So that's another way to think of this is you want to solve this set of n nonlinear equations in n variables. By the way, these equations would be linear equations if f were quadratic. So this is this is a method for solving these systems. That's another way to think of it. Okay. Now, a couple of technical things. I will not go into too much detail about the technical stuff because in the book it's pretty. What's written there is actually true. By the way, there are far more technical descriptions of it than that, but I don't believe they're needed. Okay, so we'll assume the following, that we have a starting point. You have to have a point in the domain of the function. And we're going to assume that the sublevel set is closed. Okay? Now, these are sort of, mostly technical conditions. There are a few real problems where you would have things like this wrong unless you're very, very careful about it. One would be entropy, but we'll get to those later. Now, when all sublevel sets are closed, that's easy to work out. That basically is the same as saying that the epigraph of f is closed. And in fact, some people just call f then a closed function. So that's standard notation in convex analysis, to call f a closed function if its epigraph is closed. And this would be true, for example, if the domain is everything. So that's one case. And another case is this. If f goes to infinity as you approach the boundary of the domain, Has another name. It's called a barrier. But this is another condition that does the trick. Okay, so for example, 1 over x is going to be closed, defined on x positive. That's closed. Because as you approach the boundary of the domain, which is 0, from, of course, positive x, the function goes to infinity. So that's one. Okay. So here are some examples. This one is easy, log sum exp of a bunch of affine functions. That's closed because, in fact, the domain of this is everything. So that's automatically closed. This function is much more interesting to understand why this has a closed sublevel sets. First of all, the domain is not everything. The domain is an open polyhedron here. So it's the set of points x for which AI transpose x is strictly less than bi. So the domain is an open polyhedron here. By the way, the condition that we know in x0 in dome F is not trivial in this case, right? Because, in fact, to find such a point, you'd have to determine if a certain polyhedron has non-empty interior and produce a point in it. So some of these assumptions here are not, I mean, they can have real implications. That's the case here. Now, in this case, if you approach the boundary, means you approach the boundary of the polyhedron. It means that one of these terms, bi minus ai transpose x, goes to 0. If that happens, the associated log term goes to minus infinity, and with a minus sign, it goes up to plus infinity. So this satisfies the second condition for sure, and therefore this has closed sublevel sets. Okay. By the way, it's interesting because when someone says, "Could you minimize this, please?" You could get very confused, and you could say, "I can't do that yet. I'll be able to do it next week when we look at how to solve problems with constraints." And you'd say, "That's not an unconstrained problem." And someone else would say, "Well, why is it not unconstrained?" You say, "Because you have the constraint. AI transpose x has to be less than bi. These are constraints. There's no way around that. And yet, minimizing this we're going to discuss it now, and it's going to work just fine." Okay? And the reason it is, well, we'll see why. So in fact, minimizing this is an unconstrained problem, even though you might imagine it has constraints. These constraints will be taken care of automatically. And if you want a rough idea now of why this appears to have constraints, but in fact can be considered as and solved by unconstrained optimization methods, the reason is this. A problem like this, the constraints could never possibly be active. So in a sense, they're really not there. That's the sense in which they're not there, right? You certainly couldn't minimize this and find out that AI transpose x equals bi. Whereas the essence of a constraint, for example, in a linear program or anything else, is that when you solve it, some of the constraints will be active. So that's the difference between here and here. But this requires actually some care and thinking, so you know which is which. Okay. So we're going to make some very strong assumptions, and I should say something about that. In fact, I should say something about how this all works. So a traditional treatment of all this material is you work out various proofs of convergence of things like this. That's fine, just to get a rough idea. It turns out these things are not that useful in practice. And in fact, the typical convergence theorem will look like this. It'll say if, it'll have a long list of things. By the way, not one of which is actually, generally speaking, verifiable. Right? Not only that, it'll involve all sorts of constants that you don't know. We'll get to some of those constants very soon, like Lipschitz constants and things like that. Then it'll say then, and it'll have a statement that says, x converges to the optimal, blah, 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 within, and then there'll be some number. Usually they don't even tell you what the number of, there's no bound on the number of steps. If there is a bound on the number of steps, it involves all sorts of constants you don't know. Okay? So from one point of view, one could argue that such a theorem is useless in practice. And I believe that's actually a correct statement, actually. I believe that's the case. So when you then confront people who spend, let's say, 4 weeks of a class, 10, let's say, focusing only on that material, they'll say something like this. They'll say, no, we do that because it's conceptually useful. And that actually I agree with. So it's useful to know. It's great to know something converges. Even if, when someone says, how long does it take to converge, the answer involves all sorts of numbers you don't know. So it's kind of like, at least I don't know, it's a nice thing to know that if you ran it for forever, that it would eventually converge. That's a useful thing. Okay. Now, in view of this being what I believe, actually a bunch of other people also believe, is the right is the role of all of these convergence theorems, it means really, since you're not going to really be using it, you might as well use a big hammer and just make the biggest assumptions you can, because these are just conceptual, in fact. That's sort of the idea here. So we're gonna take, basically, we're gonna make the strongest possible assumptions, basically to shorten the proofs. That's why. Okay. So in that spirit, we're gonna take strong convexity. Now, strong convexity means this. It means that there's a minimum curvature, a positive minimum curvature. So we'll assume that this is the case. By the way, for lots of functions that you actually come up all the time, this is false. You know, I mean, 1 over x is a perfectly good example. That obviously doesn't satisfy this. The curvature goes to 0. But still, we'll take this, and we do it just to simplify the proofs, because there's no reason not to, in my opinion. So you take this. This means there's a minimum curvature. Now, there's a couple of implications. I'm not going to derive these, although they're quite simple. In this case, this is what it means to be convex. This says, if you look at the function value at another point, it's bigger than or equal to, well, look, this thing over here is nothing but that's the first-order Taylor approximation. And it says basically the function is above that. Okay? If you add this thing here, it's actually in fact, it's not at all hard to prove. You write out the second-order term here and use the mean value theorem or whatever they call it and plug in some value, and you'll get this. And this says you're bigger than or equal to the first-order Taylor series. This says is a minimum curvature away from it. This says when you move away, it's not that you move away, there's a linear thing and you're above that linear thing. It says there's actually a quadratic. This is a quadratic here in y. And it basically says there's a quadratic that you're above. So it's a strong assumption. Of course, that implies all sorts of things. It implies that the sublevel set is bounded. It also implies, although it's not, it's a couple of lines to derive it, the following. It says that if you have a point x, then f of x minus p star, that's the minimum value of f, is less than 1 over 2m times the norm of f, the gradient of f squared. Okay? Oh, this strengthens all sorts of things. You know the optimality condition is the gradient of f is 0, and that, of course, is completely consistent with this. This is now a quantitative one. And this thing here gives you a stopping criterion. It basically says that when the gradient is small, when the norm of the gradient is small, you can stop. How small does it have to be? It depends on 1 over 2m. Then you might ask the question, do you generally know m? And the answer is no, you do not. So the use of this is sort of, it's a bit, it's conceptual. It means that when someone pokes into your C source and finds the stopping criterion, which is, you know, basically if the norm of the gradient is less than some number, they say, how do you know you're close to the optimum? You would trot out this inequality. And they'd say, yeah, but I looked at your code and I didn't see any m. And how do you know m? And that's when, I don't know, then you get even more vague. And you say, well, I just made a number so small that depending on what m, you know, anyway, you try to weasel out of it. You really can't. But the idea is that justifies this. Okay. So we'll look at methods that are descent methods. Actually, there's lots of other methods. Some of the most interesting ones are not descent methods. But maybe the most widely used ones for smooth problems are all descent methods. And let's look at what they are. It looks like this. And this is following now maybe 50 or 100, at least 50, so maybe 70, 80 years of sort of tradition and things like that. It goes like this. Your next iterate is going to be the current point plus a direction, well, a vector, a displacement times a scale factor. Now, these have universally come to be called, that's like the step, I guess this is the, people call this the search direction. Now, normally if someone says a direction, they mean a normalized vector, like a unit vector, because a direction doesn't have a length associated with it. But these are generally not normalized. And then they call t the step length, even though it wouldn't be the length unless this thing were normalized in length. But still, that's what people call them. So that's what we'll call them. So, and it's generally divided into 2 steps. The general step goes like this. At each you have a point x. You calculate at that point a direction to move in, and then you calculate, it's called a line search, but in fact it's really more of a ray search because you only look for positive t. You find a positive step size, and then you update like this. Oh, by the way, usually in finding a descent direction, if the gradient of f is 0, then you terminate, right? And you don't generate. So this, when you determine a descent direction, part of that usually is something that checks a stopping criterion or something like that. Okay, so this is the general method. Now these search directions have to make a negative inner product with the gradient. So in other words, if your function looks like this and the gradient looks like that, then it says that your search direction has to be sort of in this open in this open half space over here. Now, by the way, when I draw this picture, there's one thing that your eye goes to immediately, and it just seems like, how could you beat it? And that's the most obvious search direction there is, which is the negative gradient. We will get to the search direction in a minute. Right? I mean, that's sort of like, well, why would you not go, if the gradient is the direction in which locally the function is increasing as rapidly as possible, why on earth would you ever not go in the direction of the negative gradient, which is, after all, where the function is, it's the direction in which the function is decreasing as fast as possible. We'll see there's extremely good reasons for not doing this, that this is often an exceedingly poor direction. But we'll get to that later. And I mean, it's not a big surprise if you conceptualize it the right way. Okay, so that's a descent method. Now, in the line search, you have to determine a step size. And again, there's lots and lots of types of line searches, you know, hundreds and hundreds of articles and books and chapters, and it goes on and on and on. And it turns out, actually what's kind of weird about it is that for line searches, it turns out, and it's something actually I frankly don't really fully understand, but I accept it as an empirical thing, and that is that the actual line search matters much less than you'd ever imagine, right? So here are some extremes. An exact line search actually says once you point on the direction and you have a ray, you actually sort of plot, you work out what f is along that ray. In fact, for all practical purposes, you've reduced your problem to a one-dimensional problem. One-dimensional problems are easy. You plot it and use your eyeball. I mean, that's clear, right? It goes like that. If it just keeps going down forever, you found a direction of infinite descent. If it points up when t is positive, it means you need to fire whoever wrote the code that generated the search direction. So basically, this is what. So an exact search would give you this point here. And you'd think, well, look, that's the point, is to minimizing f. That's got to work well. But the other one, there are lots and lots and lots of line searches. But at the other extreme, there's something that's embarrassingly simple, and it goes like this. It's really, really dumb. You start with a step of 1. Okay? And then what happens is you repeatedly multiply by a constant beta. Beta is typically a half or something like that. So you try a step of 1. And you try it. Then you check. This condition here is sometimes called the Armijo, or which I think it should be called the Armijo-Goldstein, or really the Goldstein, since it's from Moscow. And it's almost certain that that's where this came from. But so this condition says this. It says that when you evaluate f of x plus t delta x, and let's actually look at a few things. Let's put alpha equal to 1. This is the derivative. This is a directional derivative of the function along. In fact, see this function right here where I erased the alpha? This is this. And actually, by convexity, this condition here will never happen. It cannot. That's the point. This thing here is a lower bound on that. So you'll never get a decrease as good as that. So for example, if this number here is like, 0.6, and you try a step size of t equals 1, this predicts that f will go down by 0.6. But it cannot go down by 0.6. It can go down by 0.599 or something like that. It cannot go down by 0.601, that's for sure. Okay? So you have to degrade how much reduction you want. And in fact, what this does is you multiply by alpha, which is between 0 and a half. We'll see why a half later. but you multiply by this, which says that you're going to accept some fraction of the predicted descent reduction, and that's this. And what you do now is you start at some t, you multiply by half like this until you lie below this dashed line. Now this is incredibly crude, and with things like beta equals 0.1, it's embarrassingly crude. It basically says try step length of 1. If that doesn't work, try 0.1. Try 0.01. Try 0.001. I mean, you could hardly be said to be examining, a variety of step lengths. Okay? Now, you would imagine that, like for example, an exact line search would work way better than a line search where beta equals 0.1. Right? I mean, you can only do like 3 or 4 steps or 5 or 10 steps of a line search with beta equals 0.1, because after 10 steps you're doing 10 to the minus 10, you're looking at 10 to the minus 10 steps, and at that point you might as well quit. Here's the shocking part, actually. Exact line search, works a little bit better often, sometimes. In many cases, it doesn't work any better at all. And in fact, it seems to be completely, almost independent of these parameters alpha and beta. You can take, I don't know, beta equals a half, beta equals 0.8, 0.1, and it, generally speaking, doesn't make a whole lot of difference. So it's a very odd idea, but it's borne out by lots and lots of empirical evidence. So this is called backtracking, this method, and that's the idea. So, and what happens is you get the first point when you multiply by beta that lies below this critical value t0. t0 is the first point where you get equality in this thing. It's where this line intersects the actual function there. Okay, so that's the picture. These are the line search types. Okay. Gradient. I should actually mention one important thing about line searches, since you will be implementing one. By the way, I mean, as I said earlier, we're talking like 6 lines if you put a lot of comments in and make this as verbose as you can. Okay, we're not talking a complicated thing here. One thing very important is this, is f can have a domain that looks like that. Okay? Here. And if this is t equals 1 here, I mean, this is kind of obvious. By the way, this thing works perfectly provided your function returns the right thing. If you evaluate this thing and you're out of domain, if it returns plus infinity, everything is cool, because there's no way then this inequality is interpreted as false, because there's no way infinity is going to be less than anything, right? Okay. Now, on the other hand, if you write slightly more sophisticated code, you could write one where if you ask for what is f of x plus t delta x, and this is out of domain, it will actually pass back an OOD token, which means out of domain, in which case you'd have to write some logic that fixes that. Now, unfortunately, in many cases, that's not going to happen. The worst part is that your function actually will, although you're outside the domain, that has to be added there specially. I mean, for example, you take 1 over x, and we're only looking at x positive. Okay, I can check if 1 over x, if I step out of the domain for 1 over x, so that's this thing, I'm here. What would happen is it'll make sense. It'll be a negative number. It'll be a negative number, and this is going to work. Everything's going to work, and you'll never recover from this. So this is just a hint for your stuff. So that's all right. I've said more than enough on that. Okay, so now we get to gradient descent method. It is the most obvious method. It's the first thing anybody would think of. I would hope it's the first thing anyone would think of if you wanted to minimize a function. And it just says this. Here it is. It says take the negative gradient direction. By the way, this is a classic greedy algorithm in the computer science sense, because basically it says you want to achieve a goal, which is to minimize f, and it says instead of considering, what's going to happen in the future, you simply look at that iteration and make the maximum progress towards your goal. This is literally the greedy algorithm for minimization. Okay. Now, once you put it in that context, you can imagine now it might not be a good idea, because some greedy algorithms work. Some work well. In other words, they give you actually algorithms that work very, very well. as well as any other. And some, of course, don't work at all. So we'll see this is sort of closer to not working at all. It works in a theoretical sense. So here's what you do. You choose a negative gradient. You do a line search. And the stopping criterion would typically be that the gradient is small. So the exit criterion would be actually somewhere here checked in step 1. So it turns out, I'm not going to go through the details, which is in the book. It's this. It turns out you can show that this converges. With exact line search, backtracking, it just works. And not only that, it converges with exponentially. Okay? So that means that your suboptimality, that's the difference between f and the optimal value of f, goes down by a factor less than 1 at each step. Okay? Now, that's pretty good convergence, exponential convergence. And this would be, this is sort of, usually you'd say, well, that's great. Now, it turns out actually, and you'd think, well, look, it doesn't get any better than that. I have a simple algorithm. It's totally obvious. It makes perfect, it's what anyone would do. You have exponential convergence. You would tout that. That would be like a big, big fancy thing. Turns out in practice, it can work absolutely terribly. But let's look and see how that works. And this is really sort of, the one non-obvious fact. There's a bunch of non-obvious facts, but not that many in this whole course. This is one of them. That if that it's not obvious that the first thing you'd ever do, why it works poorly or that it should work poorly. But let's take a look and see. So here's just a quadratic problem. Obviously, we know what the minimum is. The minimum is 0. That's clear. But let's just run the algorithm on it. Well, when I minimize this, I can work out the gradient. I can actually work out exact line search and so on. And you can actually just analytically work out what the points are, what the iterates are. So they look like this. Okay? And indeed, they converge to 0 geometrically, exponentially, as we were told they must. Now, the problem here is gamma, which, by the way, is the condition number of the quadratic form here. That's exactly what gamma is. Sorry, if gamma is bigger than 1, it's the condition number. If gamma is less than 1, this is 1 over the condition number. Okay? 1 over gamma is the condition number. Then it says that you go like, actually, the kappa minus 1 over kappa plus 1. It means something like that. Now, if your condition number is 10, that's fine. You multiply by 0.9 each step. If your condition number is 100, it means that you're only making 1% progress. And if it's 10,000 or 1,000,000, it means you're making very, very poor progress at each step. So that's and this is, by the way, this is not a bound. This was a bound. You can always hope when you have a bound that things can be better than the bound. And in this case, they're not better. They're right on the bound. And if you actually look at the iterate, you can sort of see what's happening. What happens is this. You're here. By the way, this is for gamma equals 10. That's a very small condition number. You're here. And so the direction, that's the gradient, and it gives you the direction of most rapid local increase. It's the most uphill direction. You go in the most downhill direction, and notice that it's pointing kind of in the wrong place. So you go along here, and then, of course, you minimize along that line. Now, when you minimize, you're orthogonal to the gradient here, and that's here. So you actually overshot. And so it's actually very useful to visualize this in 3D. So you imagine the function coming up like this, and you sort of take a ball or whatever, and you roll it. It rolls down. And actually, when it hits the minimum, by the way, is not in the valley. Everyone here, you would know how to do this, right? I guess if you're flying in an airplane above this and look down, you know exactly what to do. It says you go down to the valley and then go down the valley, because that's what this is, right? Now, instead, that's actually, when you're at the valley, it turns out you're still decreasing going this way, right? So this is and you end up doing this. Now, this is for gamma equals 10. So when gamma equals 100 or 10,000 or something like that, you get very, very slow convergence. Okay? Here's a non-quadratic example, and you can see here with well, in this case, actually, the backtracking line search actually worked the exact line search, I guess, worked quite well. But just to show you just a rough idea of how this looks. Let's look at some bigger problems to see how this scales. Here's a problem that looks like that. And here you can look at it, and these are the two things. This is the and the things that there's just a few things that matter here. Actually, the first thing that's actually interesting is note that up until about, I don't know, 100 iterations, the backtracking line search did better than exact line search. Okay, so that's weird. Actually, the reason is you don't really want to be. You can see here that actually being sloppy in your line search here would be an advantage. In fact, if your line search here were foreshortened, that would actually be very much in your favor. In other words, if you didn't go all the way to the minimum, it would actually be way, way better because you'd end up closer to sort of this axis here. And then on your next step, you'd shoot right in. So the first thing here is you see that there's basically not a huge difference between the backtracking and the exact line search, which is weird. The other thing is you can see it's taking it's taking hundreds of iterations, although I guess it's getting a reasonable accuracy. And you can estimate C from this. The other thing you see is, roughly this is I mean, just very crudely, that's like a line. And a line here, since that's a log axis here, means that you're reducing your error, or your suboptimality, by kind of very roughly speaking, a fixed fraction each step. And here you can see if you do, I don't know, let's do it this way. Let's say you do 100 steps, and you reduce it by a factor of 10 to the 4. So 10 to the 4 by, I guess you have to take logs or something like that to get the right number in 100 steps, but I don't know what that is. It's, can anybody do the log real quick in their head? I guess not. You could figure it out. But then you'd say something like C is 0.999 or something. Actually, it's probably like 0.99 here or something like that. I mean, it's easy enough to figure out what it is. So this, and by the way, this is referred to as linear convergence. Because it means that each iteration you improve your you multiply your suboptimality by roughly 0.99 or something like that by some number. Okay. We will get to a bit more about that. Now, generalization of that is the steepest descent method. The steepest descent method says, I have a norm, and I want to minimize. I want to find the steepest direction of descent. So what you do is you simply you look and you say, I want to minimize the gradient transpose times v. So v is my direction I'm going to go into. That's the directional derivative along x plus tv. That's what this is at t equals 0. But obviously, this has to be normalized, so v equals 1. So this would be the search direction. Now, it's usually unnormalized. It's unnormalized. You scale by the dual norm of the gradient. You don't have to worry too much about this. So the steepest descent is just basically so you know what it is and all that. But it's not going to be key because we're going to focus on something else. Okay. Now, the interpretation here is that in this norm, you get this. This tells you sort of the direction where, for a unit step in that direction, the first order prediction of decrease is maximized. Yeah, and actually, it's a weird thing to think that it actually depends on the norm, and that's actually the key to understanding everything. Is that if you would imagine that if you're sort of on some surface and you ask someone which way is the fastest way to go downhill, everyone would point in the same direction. Well, it turns out obviously, if the norm is agreed upon, everybody does point in the same direction. It depends on the norm, which is very weird. So if someone's using like an because the difference is this: when you say fastest, decrease of direct, you really mean decrease in f divided by, say, the number of meters you move. But meters is measured in some norm. And if people use different norms, the denominator is going to be different. And they're going to choose different directions to be the steepest descent. So this is actually, once you understand, that's actually the key to understanding everything we're going to do. Okay. So now the convergence is something like the gradient descent method. And in fact, gradient descent is steepest descent in the Euclidean norm. So that's which is not surprising. Okay. So let's look at an example here. And let's actually, once you visualize what steepest descent is, you'll realize why it is that when you ask two people at the same place what's the fastest way to go downhill, they can point in different directions. By the way, they can't point they actually have to point in directions that they can only differ by less than 180 degrees. It's kind of obvious. If they point in completely opposite directions, there's some trouble, right? Or it's very good. You're already at the minimum. Well, no. They should have told you that. So, but they can point different directions. Well, let's see what it is. If I take just a quadratic norm, then it turns out the steepest descent direction is minus p inverse this. And we can actually work out what this is. You're here. And actually, I guess first you can do the following. Let's actually first work out what the steepest descent is in Euclidean norm. So what you do is you say, I'm going to move in this. I'm going to use the linearized model. So I'm going to use the linearized model. That's the negative gradient. And you say, I'm going to move in this ball to minimize grad f transpose v in this ball. And the answer clearly is right here. That it says go in that direction, which is the negative gradient. But now suppose, in fact, that you measure your displacement using this quadratic norm. This is the ball. And then it says go as far as you can in this direction in this ball. And what happens is it's here. It's actually it's been rotated over to this direction. It's been skewed over here. And so you can see these are obviously not the same direction, and you've actually twisted the thing. Now, in fact, you can't twist it more than 180 degrees because that's a positive definite matrix. And if you multiply a gradient, one vector, by a positive definite matrix, you don't rotate it more than 180 degrees. In fact, that's 90. Well, anyway, sorry, that is exactly what, actually 90, sorry. That is exactly what a positive definite matrix is. So you've twisted it over like this. It gets interesting, too, if you want to do steepest descent in the L1 norm, because you draw a ball like this and take the gradient like this. By the way, what would be the steepest descent direction in the L1 norm if this were the gradient? If that were the negative gradient, what would be the steepest descent direction? Well, what's the farthest? It's weird. It's curved, isn't it? That's kind of a weird thing. Anyway, all right. Imagining that I had drawn that arrow straight, what would be the steepest descent direction in L1? What would it be? Well, you'd go as far as you can in that direction, and so it would actually be this point here, and that would be your direction. And you can kind of make a guess about steepest descent in L1. Go ahead and make a guess as to what it's always along a unit. It's always along a unit vector, or it can always be chosen to be along a unit vector. If you're going along a unit vector, it actually has a very beautiful interpretation. It basically says you're updating one component of the variable. So if you do steepest descent in L1, at each step, you optimize over one component of the variable. Okay, so that's what that is. Okay, that's actually not our main interest is not that. It's actually has to do with the choice of the norm for steepest descent, and so this will be it will illustrate this here. Now, the first thing we'll take. Now, by the way, these are the sublevel sets of some function here. It's the function we just looked at, like this. And the point is, if you look at this function, what you see is this is very rough, but this is the idea. The function is sort of elongated. It's not spherical, right? It's kind of fatter than it is tall, roughly. Okay, that's the main thing here. If you choose a norm that is sort of aligned with the gross geometry of the sublevel sets, an interesting thing happens. You end up actually making very fast progress towards the center, okay? Because you actually end up going in the right direction. If you take a norm which actually is whose unit ball is sort of not aligned the same way the gross geometry of the sublevel sets is, it actually amplifies this effect of oscillation. Okay? So the rough idea is something like this. There's another way also to understand this, which I'll get to in a minute. The basic way to understand this is something like this. If you really want the norm that you use, if you use steepest descent, you want the norm to sort of be consistent with the geometry of your sublevel sets. Okay? So if your problem, if the sublevel sets, were sort of spherical, were more or less spherical, like that, right? By the way, if the sublevel sets were spherical, how would gradient descent work? Or nearly spherical? How would gradient method? It would work. Actually, if it were perfectly spherical, it would work flawlessly. It would say that's the gradient. That's the negative gradient. It would go in that direction. Negative gradient would point, if not to the center, to the optimizer, it would point very near it. You'd minimize it and you'd end up over here. So actually, the gradient method works perfectly when your function is, and I'll try to say this right, when it's isotropic or something like that. When it kind of extends, when it looks about the same in all directions. If it's kind of spherical, or in all directions it looks about the same. Gradient descent works absolutely horribly when the sublevel sets look like this. Okay, that's exactly when you get this sort of story. Okay. Now, when you do steepest descent in a norm, it's the same as changing coordinates and then applying gradient descent. So what you want to do is you want to change coordinates to make things that look like this look like that. So the whole key, in fact, is choosing the norm. That's the key to everything. Okay? So the norm you do steepest descent in is very, very important. Okay. Now, by the way, this already, if you just incorporate this amount, you already know a lot. If you really you actually know a lot more than a lot of people who do optimization, if you just understand just what I just said. So, for example, suppose you know something about the function you're going to minimize, right? Suppose you have samples of it or something like that. You can do all sorts of cool stuff. You could like fit a quadratic. Suppose you've already evaluated the function at like a couple of hundred points. You can fit a quadratic to it or do whatever you like. You could fit a quadratic, and the quadratic would sort of tell you which direction the function is sort of long in and where it's got steep canyons. You would then use that quadratic to fit your to change coordinates. Or if you like, you could use that metric to do steepest descent. Everybody see what I'm saying? That would work extremely well. I mean, that would improve steepest descent tremendously. Okay. Now, there's a very obvious choice, though. If you want to get, so let's see, how do I motivate this? So I'll motivate it this way. Let's suppose you're near the bottom of a function. You're near the minimizer. So here you are. It's smooth. Actually, what does the function look like near the minimizer? What's an approximation of f near the minimizer? So, well, it's equal to f of x star, right, plus grad f of x star transpose x minus x star, right? What's that? That's 0. Okay, so we go to our next term, which is 1/2 x minus x star transpose, the Hessian, x minus x star, right? So that's our next term. Okay, now near the optimum point, the optimal point, it looks quadratic. And so what did the sublevel curves of f look like approximately near the minimum? They're ellipsoids, and they're ellipsoids determined by the Hessian. So they look like this. They're ellipsoids. Hey, that's funny. That's exactly what we want, because it tells you what the shape looks like. And it basically says, if for some reason you knew that number, of course that'd be that matrix, it'd be very interesting that you knew that, because the only way to find that, I guess, would be to find x star first and then evaluate it. But suppose anything intelligent you could guess about this Hessian, it's going to tell you something about the shape of the sublevel sets, certainly in the end game when you get close. Okay? So then you can imagine, I'll do steepest descent, but I'll do it in the norm induced by the Hessian. Okay? And that brings us, that's very famous, that's called Newton's method. And that's our next topic. Okay, so let's look at the Newton step. So the Newton step is this. It's actually, in fact, well, there's many ways to interpret it. It's minus the Hessian inverse times the gradient. That's all. And you can say lots of things about it. So here's one. One way to motivate what the Newton step is you take your function and you develop a second order approximation. That's this. And then it says, I'll minimize this instead. If you minimize this, you just take the gradient with respect to v equals 0, and you'll get v equals the Newton step here. So this minimizes that. That's one way to think of it. And in fact, that's a very good way to think of Newton's method. Newton's method will use the Newton step. And it basically says you take a function, and at each point you develop not a first order approximation of the function, but a second order, and you minimize that. and then you update. So that's this. Another way to say it is this. You want to solve, if you're at the point x, you would like to find a v for which the gradient of f evaluated at x plus v, that's where you're going to step, that should be 0. But the problem is the gradient is some nonlinear function. You don't really know what gradient of x plus v is. Okay? So, all right. So what you do is this, is you say, well, look, this nonlinear function is about equal to, I'll replace it with this linearized approximation, which is the gradient where you are, plus the derivative of the gradient. But that's nothing but the Hessian. So this is that. And then you set that equal to 0. And if you solve this equation, of course, you get v equals minus Hessian squared, minus Hessian inverse gradient. You get that. And the two pictures correspond to something like this down here. So in the first case, here's f, our function, and here's our point, x. So in the first interpretation, it says develop not a first order Taylor series approximation, but a two-term Taylor approximation. By the way, when you carry out two-term Taylor approximation, convexity is preserved. If your original function is convex, so is your two-term Taylor's expansion. You know, obviously, because the Hessian is positive semidefinite. And it says minimize that. And that would give you this one, this point here. Notice that, you know, at that point already, you can see that f hat and f are not the same. By the way, what will happen in the next step here? If that's our Newton step, and I carry out this again, I fit a quadratic to this point and do it again. What's going to happen? It's actually going to be much better this time. And when I start getting near this bottom point, these quadratics are going to be extremely good approximations, and the improvement you're going to make each step is going to be dramatic. Okay? Another way to see it is this. Here's f prime, and we wanted to solve f prime equals 0. That's what optimality is. So and it's convex, which means f prime is increasing. So f prime is increasing. That's f prime. I'm here, and I evaluate the derivative of f prime. That's the second derivative. Okay? And I form this dashed line, which is in fact this thing. Okay? Which here is very simple. And I take the 0 of that. That's that. By the way, what happens on the next step? From this one, it's extremely easy to see what's going to happen. You're going to put a line through here. This is not linear here, or affine, but it's very close. And the next iterate is going to be somewhere in here. When you get in there, the iterates are going to be unbelievably accurate. And you're going to get very fast convergence. Okay? So this is sort of the picture. So, by the way, people call methods where you update sort of this matrix here, they call these, a beautiful term for this, although it means something a little bit more specific, is a variable metric method. So metric here refers to how you describe distances and things like that. So a variable metric method is a method that varies, it's essentially the norm being used in steepest descent at each step. And it adjusts it to the geometry of the particular problem instance. That's what a variable metric method is. And so, although you wouldn't call a Newton method a variable metric method, it is one in that broader sense. Okay, so you can think of all the third interpretation is this: is that the Newton step is the steepest descent direction in the local Hessian norm, something like that. So that's what it is. That's the picture. Okay, let's look at. Let's look at the Newton decrement. Now, the Newton decrement is actually the Newton decrement squared. It's defined as this. It's actually the norm. Lambda is the norm of the gradient, but in the metric induced by the Hessian. So that's what this is. That's that. And it's a measure of the proximity of x to x star. And it's actually a good one, and I'll tell you, we'll see some very good properties of it in a minute. And it allows you to make a very good approximation of how suboptimal you are. So 1/2 lambda squared is a very good approximation of how suboptimal you are. And it's basically the norm of the Newton step in the quadratic Hessian. It's also the direction of the derivative in the Newton direction. So it turns out you actually have to calculate this whether you like it or not, because that's the thing used in the line search. That's the Armijo. That's the number. This is the quantity that appears on the right-hand side of the Armijo line search anyway. And here's the really cool part about it. It's affine invariant. And let me say a little bit about that with Newton's method. Well, we haven't talked about Newton's method, but I'll say something about that in a minute. But let's, yeah, okay, let me give Newton's method, and then I'll come back to this. So Newton's method, very, very simple, looks like this. You're given a starting point and a tolerance or something like that. You compute the Newton step and decrement. You know, obviously here, if lambda squared is small enough, you quit. That's fine. Otherwise, you do a line search, and then you update. That's Newton's method. All right, now, what we'll find out is that this works unbelievably well, shockingly well. We'll take a look at it. We'll see in a minute. But there's a couple of reasons. There are many reasons. One, I think probably the best zeroth order description of why it works is affine invariance. So let me explain what that is. If you want to minimize f of x, I'll try to get the notation here right. Okay. I could change coordinates and let ty equal x, where t is a non-singular matrix. And I could just as well minimize, you know, f of ty over y. Obviously, I could do that. Change the coordinates. Okay, but there's a little bit of a, and then you ask about, well, what if I apply, if I change coordinates and then apply gradient method, for example, you know, do you get the same thing? And the answer is no, you don't. And in fact, what happens is in a gradient method, when you take, if you call this thing f tilde of y, then grad f tilde of y is actually t transpose times f of ty. Okay? So you get that. What have I done? There. Thank you. Okay? So you actually, it changed coordinates, and that means actually if you change coordinates and then apply gradient method, these don't commute. It's not the same as changing applying gradient method and changing coordinates. They don't commute. Well, in fact, that's the message of everything we just looked at. If you change coordinates or change the metric, the gradient method changes. Now, you can look at it as an optimist and say, hey, that's cool. If I only get the right coordinates, gradient method is going to work really well. In fact, we know what the right coordinates are geometrically. We want to change coordinates so that the function looks isotropic. It looks round. That's what we want. We want the function to look about the same in each direction. We don't want steep canyons. We don't want stuff like that. If it kind of looks about the same in all directions, gradient descent is going to work really well in that metric. So that's the idea. Okay. Now, the truth is, there's a lot more bad choices of coordinates than there are good ones. So with all due respect to the optimism expressed there by saying there is a choice of coordinates which makes gradient method work well, which is a true statement, there's a lot of ones that don't. Another way to say it is this. If by any chance your problem is solving well with gradient descent, and by the way, there are plenty of problems that solve well with gradient descent. Obviously, these are the ones which, for various reasons, are round, or they're not too unround, right? They're the ones where they kind of are about to. There's lots of cases where gradient method just works. For super large scale problems, you know, it's one of your only choices. So, you know, good for you if a gradient method works, right? But in fact, it's not. They generally don't work for smaller problems. And I can always just change coordinates. I can even take t diagonal, and I guarantee you, if your gradient method is working and I change coordinates, I mean, I can just scale your variables, and I will bring your gradient method to a halt. And of course, in theory, it will converge. But I can make your C 0.999999, and you're going to have a lot of iterations. Okay? Now we get to Newton's method. Newton's method, actually, you get a commutative diagram. So Newton's method and affine changes of coordinates, they commute. So in other words, if I want to minimize f of x, and I change coordinates, and I do something like I minimize f of ty here, I'll get a sequence of Newton iterates. Okay, so this is Newton. This is change of coordinates, right? I'll apply Newton, and I'll get, you know, x1, x2, you know, and it's going to converge. And here, I'll get y1, y2, and so on, like that. Okay? Now, I guess if you have any aesthetic sense at all, or have even a small training in mathematics, you have an overwhelming urge now to your hand is shaking because you want to fill this in. Anyway, so you want to fill, and that's called a commutative diagram, and it basically means it's cool. It says basically, this basically, it's called a commutative diagram because it says basically Newton's method and changes of coordinates commute. And in this case, it's correct. By the way, if I replace these with gradient method, it's completely wrong. It does not commute at all. These are totally different sequences. And from a practical point of view, this is very, very important because it means, for example, these x's could converge basically to a good enough solution in 10 steps, and this could take 10 million. Okay? So changes of coordinates and gradient method do not commute. Very important. Changes of coordinates and Newton method. What did I just say? It was wrong. That's the problem with these things being on TV. Oh, anyway. So I'll say it again, and this time I'll say it slower, and it'll come out right. I think I said, did I say it wrong? I did? I've just confused myself. Okay, that's fine. I'll go slow now. Changes of coordinates and Newton's method do commute. That was right. Okay, so they do commute. And actually, that means all sorts of cool stuff. It means, I can tell you what it means. It means to first order, scaling is a non-issue in Newton's method. In fact, it's only numerical that it's an issue. And let me explain that. In gradient method, if the condition number is 1,000 of the sublevel sets or whatever it is, you're in deep trouble because it means you will be making 0.1% progress at each step. That's what it means. That's what it means. So in that sense, you know, a kappa of 1,000 is already bad for Newton's method. For gradient method. Now, if you take Newton's method and you do everything exact arithmetic, it's just no problem. It's identical. There is a second order effect. The second order effect actually has to do with numerical linear algebra and actually solving h v equals minus g, where h has high condition number. But a condition number of 1,000 for a positive definite thing is a joke. It's basically 0 for all practical purposes. That's an extremely well-conditioned positive definite matrix from the point of view of a numerical analyst. From the point of view of the gradient method, it's basically slows the gradient method to useless. I mean, 1,000, I was drawing pictures here with 10. And you can actually visually see the ridiculous oscillation. Imagine what it is for 1,000. Okay? And in a lot of dimensions where you can't visualize it. Anyway, it will be very, very slow. There'll be lots of oscillation and stuff like that. And it'll basically be unusable. But for Newton's method, no difference. Absolutely no difference. It'll just run perfectly. Okay, so that's the idea. So let me tell you a little bit about the convergence analysis of Newton's method. So Newton's method, first we'll look at the classical one. This is Kantorovich. You'll never guess where he was a professor. I'd say your first guess is right, actually. So this is, although I'm not pronouncing it right, but I'm sure there's people here who speak Russian who can tell me how to, but that's how I pronounce it, and I don't know. So it's like Gauss or whatever. I'm probably not pronouncing that right either. Anyway, okay. So here are the assumptions. We'll make F is strongly convex on S with constant M, and the Hessian is going to be Lipschitz continuous. Now, by the way, this is essentially a constraint on the third derivative of F, right? Because it's basically saying how fast can the second derivative change. You can interpret L as a limit on the third derivative of F. Now, let me tell you why we don't do it that way. Because what is the third derivative of a function from Rn to R? Here's your hint. Only people in mechanical engineering and physics would not be bothered by what it is. Thank you. That's a tensor. It's a trilinear form if you're in math, or it's a tensor. It's got 3 indices and all that kind of stuff. It's not fun. I guess actually, if you're fully trained in all these things, I think it doesn't scare you at all. It's no problem. In which case, all I have to say is good for you. So anyway, it's easy. All we need is a bound on it, so we'll just put it this way. So by the way, you can imagine, before we get into this, let me ask you some questions. How well does Newton's method work on quadratic functions? One step. It works super well. Why? Because Newton's method does this. It takes a point. It develops a quadratic model of your function. Now, in this case, it happens to be your function because your function is quadratic. Okay? It then minimizes that quadratic function, which unbeknownst to it is your function. And then it steps to what's the minimum, and asks again, say, hand me the gradient and the Hessian, and the gradient is 0, and then it actually sends a message back, says, don't even bother with the Hessian. So it's one step. Okay, so basically, when do you think Newton's method is going to work well? Well, it should work well when the Hessian is slowly changing. So if the third derivative is small, Newton's method should work really well. Everybody kind of seeing the idea here? Because basically Newton's method is, you're basically, let's see, at each step you're minimizing a quadratic model. If your quadratic model is really good, even for big displacements, Newton's method is going to work really well. So basically, small third derivative is what makes Newton's method work. Okay? So I'm just getting you all prepped for the idea that L, the Lipschitz constant, is going to play a role in Newton's method, and the Lipschitz constant on the Hessian is indeed a bound on the third derivative. And we know, at least in one extreme case, if L is 0, Newton's method works very well, one step, because it's quadratic. Okay? All right. Now, here's the way Newton's method, the classical analysis works. It's going to work like this. There's going to be two regions of sort of convergence, and it's going to work like this. If the norm is bigger than some number, and it's some positive number, so then what's going to happen is f, you're going to be guaranteed at each Newton step to decrease f by a constant, just an absolute constant. Okay? Now, by the way, that means that this step, if f does have a minimum, this step cannot be executed more than some number of times. Because basically, it says you guarantee a decrease of, whatever it is, 0.26 at each step. But that means if you make k steps, you have reduced f by 0.26k, so you can't go too, if you went infinitely off in doing this, you'd have a minimizing sequence going to, it'd be unbound below. Okay? So that's the picture. Now, so eventually, the gradient gets smaller than something. Now, once the gradient is smaller than some number eta, you have the following. And you have to look at this very, very carefully. It's got a constant L over 2m squared. Don't worry about that, but look at this whole thing as a measure of error. That's a measure of, it is a scaled residual. And this says that the residual is less than the residual squared at each step. Okay? Now, by the way, once this number, let's suppose at some point this number becomes 1/2. Just for example. So this number gets down to 1/2. It says on the next step, it's less than a quarter. And on the next step, it's less than a 16th. And then 1/256th. And then 1/256 squared. Everybody see? So the point is, the convergence then is extremely fast. You're basically, once this number, it basically says the error is squared. It's all very rough, but it says basically the error gets squared every step. Once that error is small, that's a huge reduction in the error. Compare that to saying the error gets multiplied by 0.99 at each step. Huge difference. Okay, so let's look at how this works. Now, when you're in the so-called damped Newton phase, damped Newton means, we'll see. It means you actually require backtracking steps. It means that a full Newton step, you actually have to backtrack from t equals 1 to whatever, something. And the function value decreases, it has to decrease by at least gamma. Now, as I said, if the function is not, if it's bounded below, this has to end after at most this number of iterations. That's obvious because at each step, otherwise, if you ran more than that number of iterations, you would have reduced the value of f to below its minimum value, which is not possible. So that bounds the number of steps you take in this stage. Once you get into the so-called quadratically convergent stage, it basically says the following. It says that this thing here is less than 1/2 to 2 to the L minus k. So that's how that works. So this is for L once you've gotten to that point. So at this point, you're actually, this is, many people say this many ways. One way is to say the error is squared at each step. Not quite true. Another way is to say the number of accurate digits doubles every step, because that's what this says. Well, this says it in bits, actually. Okay, so the number of accurate digits doubles. Now, of course, most normal people use doubles and floats, IEEE floating point. So this is amazing, but it basically says that you can't execute this more than about 4 or 5 times. before you get to double precision stationarity. At which point, normal people say you're done. You're actually done. Okay? So if you work out the global complexity analysis, it works like this. It says that the number of iterations until you get less than epsilon is less than this. That's the initial phase. And look, it depends on like how bad your initial point is. So if your initial point, I mean, basically, actually, it depends on how suboptimal your initial point is here. And then there's the second term. This is the quadratic term. This is log epsilon 0 over epsilon. Epsilon 0 is one of the, it's just a, it's a constant. So this is it. Now let me explain a little bit. So actually, I go around and give talks often about things like this. And what I do actually when I do that is I actually give talks and I replace this with the number 5. I'm just baiting people. All right? So it's for me to torture complexity theorists, right? So I wait, I just keep going with the 5. I'll even stare right at somebody I know. Just kind of look at them right in the eye and I'll say plus 5. Just baiting them. And finally somebody takes the bait and they'll say, excuse me. And I'll say, oh yes, did you have a question? And they'll say, yeah, you can't solve that problem exactly. So what happened to the accuracy epsilon, huh? I don't see epsilon in there. And I say, oh, sorry, this symbol 5, that's how I write log 1 over epsilon. So from now on, whenever you see the number 5, it actually means log epsilon 0 over epsilon. Is that okay? Because that's how normal people write this expression, is 5. Okay, so it works pretty well, actually. But they do fall for it pretty often, actually. So, all right. But actually, so the interesting thing about this, actually, is it says that to a normal person, it basically says that, actually, well, let me ask you this. How does the number of Newton steps required, and I'm talking by the theory, even by the theory, and by the way, in practice, it's even stronger. How does the number of steps of Newton iterations required change with the accuracy required? So, if you're in a court under oath, what would you say? You would say, very, very slowly, log 1 over epsilon would be the answer. But any other place, what would you say? You'd say, not at all. And someone would say, really? The cost of computing a super accurate answer is the same as like a crude, sloppy, terrible answer? By the way, for gradient method, those two numbers are grossly different, right? Because you pay for gradient, it's hard work. You keep multiplying by some number that's 0.99, and you have to do it a lot more times before you drive something to an error that's like 1e minus 8 or 1e minus 12 or whatever it is, right? It's going to cost a lot. For Newton's method, it's basically costless. Everybody see what I'm saying? So okay. So that's why, by the way, people don't worry a lot in practice about what's the stopping criterion for Newton's method. Because roughly speaking, it's this. Once you're into the quadratic, because the cost of calculating a super accurate solution is essentially like 1 or 2 steps more than calculating an okay solution. So it just doesn't matter. That's one way to say it. Okay. Okay. Now there is one minor problem. There's two minor problems with this classical convergence analysis, and I'll say what they are. The first is that obviously this goes back to my comments before. Obviously, in any particular problem, you have absolutely no idea what L is, number one. You have absolutely no idea what M is. Now, the other things appearing in here, like in gamma, you have to have alpha and beta. These are the line search parameters. You do know what those are because they're in your code. Okay? They're in you just look through your code and you'll find them. So, but you don't know what M and you don't know what L is. That's ridiculous. Right? So, the point there is this is still useful because you will observe sort of a damped phase and then a quadratically convergent phase. So let's look at some examples. Here's an example of Newton's method for that problem before. And you want to notice two things in this example. You want to notice actually the axis here, and you want to notice the axis here. And by the way, here you see, let me show you what you see. You could argue, I mean, look, it's 5 iterations, so the point is, but here, you have this region, something like that, you would argue maybe here, it's sort of, it is the damped phase. You have to see this. you have to see this thing roll over for Newton method. You will implement one this week. Actually, the next 2 days, right? It's Tuesday. So you will, if you don't see this thing rolling over, you're not achieving quadratic convergence. That's what it means. Okay? It is possible, actually, that quadratic to have this look kind of flat and then roll over later, but we wouldn't assign something like that to you because it would give you the wrong message. Generally speaking, if you see it flat, by the way, if your plot looks like this, yeah, then there's something really seriously wrong, okay? But if you don't see that, you're not doing Newton's method. Also, these are about the right numbers here. And you might ask, how does that scale and all that kind of stuff? And you would see something like this. This is an example in R100. Again, you can note the axes. And again, exact backtracking line search just saves you 1 step or something like this. And if you want to know how does this scale, here's an example in R10,000. And it's very close, I think, to what you might be doing anyway. So here, actually, you can see it quite clearly. So this is in R10,000. You're minimizing some smooth convex function. And in fact, you might argue that quadratic convergence goes into effect somewhere around here. Something like that. I mean, who knows, but that's roughly what it is. This is what you see. So you might you'd have like 13 steps, and then once you hit quadratic, you'd go 6 more and it's all over. And you get something like this. This is an R10,000. That's a big place, by the way. And you might ask, what does this look like in R10 million? And the answer is, it looks exactly like this.
Computing the inverse Hessian compared to the cost of the extra steps you'd have to do.
That's a very good point. So let me actually say something about that, because that's a great point. Also, I'll short circuit a whole section of what you'd hear in other classes. Okay, so you should notice this axis. It is completely unfair to compare this axis to the one in the gradient method for precisely that point. Each step here requires solving hv equals minus g. That's how you calculate a Newton step. Okay, so in a dense case, the cost of that is going to be n cubed. The cost of evaluating the gradient and all that, we could maybe make it n. I mean, it depends on what the problem is and all that, but let's just say it's n or something if it's simple. It'd probably be more likely n squared, but let's make it n. So then you actually have to take that into account, at which point you'll actually still find the following. If you need high accuracy, nothing will beat Newton. So that's it. Now, by the way, there's a whole family of methods in between gradient and Newton. And these came into being in the 60s. And they came into being because solving, for example, there are even very famous people who said things like, no one will ever have to solve. It wouldn't even make any sense to solve 100 equations with 100 variables. Right? It just doesn't make any sense. No, there's never a time when 100 things could depend on 100 other things. And besides, there'd be 10,000 coefficients in there. You see what I'm saying here? Right. Okay, so it'd just be inappropriate to solve ax equals b if a is as big as... I mean, we're talking iron core memory days, which means nothing to any of you. And by the way, it means nothing to me, too, just for the record. But still, this is in the day when it was a big... The n cubed was a very scary thing when n was 100. Okay, for you, n cubed doesn't start getting scary right now, this year, until n equals 2,000. And it's not even that scary, right? It's not that big a deal to make it go a bit higher. It'll start getting scary at around 5,000, 10,000. That could get scary. But that's what 100 looked like before. So in those days, all sorts of they worked out all sorts of methods where to avoid getting out of solving hv equals minus g, they avoided the n cubed trick. And they did things like they would update h by a heuristic and stuff like that at each step and so on. And there's lots of methods. By the way, some of these methods are quite good and they actually do have their uses. We'll look at them next quarter. And these are called quasi-Newton methods. They have all sorts of names like this. So I have a couple of comments about it. So the first is this. In terms of the cost of the Newton's method. If you don't know how to solve linear equations, and I'm sorry to report that many, many people do not know, then they overestimate what it costs to solve HV equals G, this thing, HV equals minus G. Okay? So when you're more sophisticated like you are now after last week, and H is sparse, banded plus low rank, if it's got toplet structure, anything like that, you will realize that all of those tricks can be brought to bear here. So I think one of the things is you have to remember that in many problems, when you compute the Newton step, there's lots of structure lying around in real problems, lots and lots. And if it's exploited, which is to say that you do your linear algebra intelligently as opposed to stupidly, you'll find often that the cost of Newton's method is entirely feasible, even in things like signal processing problems, image processing problems, where the number of variables is 1 million or more. You find you can do Newton's method, even though if you couldn't, obviously you couldn't even remotely write down the Hessian and store a Hessian in a signal processing or image processing problem, or a large machine learning problem. You couldn't do it. But if you know what you're doing, you can actually solve these equations, shockingly. So that's a long-winded answer to this. So it's not 1963, in which case the rest of the quarter would be methods for avoiding using Newton's method at all costs. It's not. So things have changed, and now Newton's method is just not a big, it's just not a big deal. And especially coupled with if you know how to solve linear equations intelligently, then a lot of times the cost of Newton method drops right down to the quasi-Newton methods from the 50s and 60s. So, okay. Well, we'll quit here and have fun, because you're going to do all this.